Well, it is that time. Welcome to Analyst 3. If you just got here, please, and you're in the room and not joining us on Zoom, please fill out the attendance sheet so we can know who is here. There was someplace, I don't remember where I was going with this. Doesn't really matter. Real quick, how has the first week and a half of the semester gone? It's been weird. I'm not gonna lie. It's been really weird. Like, normally by this time of the class, I know people's faces and I'm starting to associate names with faces. I have like half faces now. I'm not even sure I'm gonna know anybody's name really by the end of the class, because I'm not sure I'm gonna know who you are to come into my office next semester, which is sad. But that doesn't mean we can't still do some fun things this semester. So it'll just be a little bit different. That's what I just keep telling myself. It's just gonna be like normal, but a little bit different, and that's okay. Thank you for filling out the first week's reflective writing assignment. I enjoyed them greatly over the weekend, reading them and getting to know you guys a little bit better, even if I don't know your faces. I didn't comment. I did read them all. I didn't comment on all of them, but I did comment on a lot of them. So I don't know if that shows up in your feed, but if it doesn't, you can go and check and see. Sometimes I've written you a little comment in there. But I did read them all, so thank you for doing that. There's another one up this week. Has anybody looked at it yet? Is it the advice one? I think it's advice. So this week is looking back on your first year of physics. What would you give advice to someone who is just starting Analyst 1 on what they should be doing? And take this serious. I'm actually teaching a first year physics experience class this semester. I actually will share your responses with that group. Give it a little bit of thought. Not a lot of thought, but a little bit of thought. New timing for all of that this week. Kappa will be due Thursday at midnight. That response will be due, I think it's due Friday morning by like 8 o'clock. My thought is, whenever you finish the physics homework, whenever that is, take 10 minutes and fill out the question of the week. So questions about any of that? Yeah. There is not, but I will set that up. I will put a little Dropbox there. You're certainly welcome to bring a paper copy and put it on the desk here. Probably bad COVID response. Maybe it's better to set. I'll set up a Dropbox. That's probably the preferred way to submit those. If you really don't want to do it that way, I will take a paper copy. But yes, I will set up a Dropbox on. And if I haven't done that by like tomorrow morning, somebody send me an email and remind me to do that. Good question. Okay. Great. Let's get started. So we have did a review of Analyst 2, talking about Maxwell's equations, and we have thought about, in a vacuum, in a region without any charged particles at all, is there a series of fields that could satisfy Maxwell's equations? First, how are Maxwell's equations changed? And second, are there a series of equations and waves and fields that we can write down that does satisfy Maxwell's equations, even in the absence of any charged particles, that isn't just the trivial no fields exist here? Because the zero field case would satisfy Maxwell's equations because there's a zero on both sides. But that's not an interesting case. There is an interesting case where we can satisfy Maxwell's equations with non-zero fields. And that's what we're going to be investigating for the next week or so. And we wrote down some equations for these waves. Let's just write them down again so we remember what's going on. I'm going to close this attendance thing. That can go up here. I'm going to make this go very small. Okay, good. Now we're back here. Okay, so the fields were this. The electric field, again, it's a vector, some amplitude in the j hat direction, times sine of kx minus omega t. And same for the B field, almost exactly the same, except it's in the z direction. And those are the set of fields we talked about. We had a little bit of a visual on what those fields look like. This is basically it. The waves are propagating in the plus x direction. The magnetic fields point in the z direction, electric fields point in the y direction, and they are sinusoidal. They are constantly varying up and down. Not up and down, in magnitude, both in the up direction and in the down, the positive direction and the negative direction. They are in phase. Where there's a maximum in the E field, there's always a maximum in the B field. There's a minimum, there's always a minimum. When there's a node, there's always a node. They are traveling at the same speed. These wave properties are almost exactly, they are in fact identical. This is a slide from Holliday-Resnick-Walker that shows the cycle of these magnetic fields at a given, and electric fields at a given point. This looks like a cycle and looks like we're moving around in a circle, but really you're talking about the behavior of the fields at a given point that's called P, from greatest magnitudes in this direction, E and B fields, to smaller E and B fields in that direction, to no E and B fields in that direction, to small E B fields in the other direction, to the maximum, to smaller, back to zero again, and then back to maximum. So again, this is a cycle that shows at a given point what the magnitude and the directions of those magnetic fields look like. It's a sine wave. They just go up and down in the different directions. Okay, great. So examples, problems, we can't do much without the differential forms of Maxwell's equations. So instead, we're gonna do in class, we're gonna prove that these laws do in fact satisfy Maxwell's equations for a couple of different scenarios. And that's gonna help you with the written part of the homework for this week also. So let us start with proving that Gauss's law is satisfied, that these fields satisfy Gauss's law. So, reminder of what Gauss's law is. It is an integral of the electric field over some surface. Again, there would be some charge term here if we were in a non-vacuum. Since we're in a vacuum, this just becomes zero. Okay, let's start with a simple, so we can, again, we've got this huge volume. We can pick any surface we want to, but let's pick a simple surface because that makes our life easier. Let's think of a cube in this volume. So let's draw a small cube. This can be test my cube drawing abilities here. That's not a bad cube. I've drawn much worse cubes than that in my day. Okay, so I'm gonna actually go ahead and draw that's the front of the cube. This would be the back of the cube. That's not bad. There's our cube. Okay, let's set these up in the normal axes. Let's call this the x-axis. Let's call this the y-axis. Let's call this the z-axis. X cross y equals z. Be careful when you're drawing axes. Again, it doesn't really matter how you draw it, although you'd be crazy not to draw it this way, but you don't want a left-handed coordinate system. You want a right-handed coordinate system. What does that mean? Right-handed coordinate system means that x cross y equals points in the z direction. If you don't have that, then everything's messed up. Your coordinate systems are just wrong. So however you draw it, make sure that x cross y equals z. And that's the way this works. Okay, so we only care about the electric field. In which direction so we've got 6 sides of this cube that we're gonna have to worry about. We have to worry about what the electric field is, because this is a surface integral. We're going to have to calculate the integral over all 6 of these sides. Which direction, though, does the electric field point? No, good guess, though. The wave is moving in the x direction. Which direction is the electric field point? In the y direction. The electric field is pointing in the y direction. The magnetic field is pointing in the z direction, and the wave is moving in the x direction. Right? Okay, so let's think about this dot product. This dot product is going to help us, because let's pick a side. I don't know, let's say the right-hand side over here, this one. The electric field, and again, we don't know if it's pointing in the positive or the negative y direction, but we know it's pointing in either the positive or negative y direction. What is E dot dA? Where is dA point for the right-hand side of this cube? To the right. The vector, the area vector, is always perpendicular to the surface of the area itself. So the A vector, the dA vector, points in that direction. And that, what is E dot dA for that surface? It is 0 over anywhere on that surface, because the electric field is always perpendicular to the area vector. And that cosine theta term goes to 0. That's also true of this side. What about the front and back? Also 0. Again, the E field points up, the A field is pointing either into or out of the board, and perpendicular. So front, back, left, right, 4 of those sides equals 0 without, just because the dot product is 0. You don't have to think about it. It's 0 everywhere along those sides. The only ones we really have to worry about are the top and the bottom. Let's think about the top and the bottom carefully. And we only have to worry about the E fields at the top and at the bottom. It's not going to matter much, but this is where the E fields aren't actually sticking out anywhere. It is just the point at the surface, the field value at the surface, that we care about. Okay? So let's think about this carefully. At every given x value, let's pick an x value. Let's just pick a point, I don't know, anywhere on the top of this surface. And let's say we know that the electric field is either pointing up or down. Let's say it's pointing up at this particular point, right? We know it could be anything, up or down. But let's just say it's up, and it has a particular magnitude, let's say there. That's our E field at that particular point. What is the E field also at the top at a different location that has the same x value, but a different z value? Let's say this point right here. That point, if we draw a little dotted line here, has the same x value, but a different z value. What is the electric field there? Let me draw these as red. Maybe that'll be a little helpful. What is the electric field here compared to the other one that I just drew? The same. Why?
Because the electric field changes only as a function of
there is
the y and the t values.
It's not even the y value. Let's scroll back up and look at these equations. If the x is the same, there is no z term here at all. There is no y term here at all. If x is the same, then the field is the same at that given time, at that given instant. So this point, that I've drawn that has the same X value has to have the same E field. And that's the same of every single point that I could draw along this point. They all have to have the same E field. What does the electric field look like at the bottom of this, at the same X position, location? Let's draw an E field for here. What is the value of the E field at that point, at this particular time? It's the same. That point has the same X value, but a different Y value, but Y doesn't appear in our equation either. So this must also have exactly the same E field, whatever it is, as the one on top. And I could draw the equivalent points over here. Now, let's go to a different X. Maybe over here, the E field is completely different. We don't know what the E field is. It depends on how big the box is and what the frequency of our wave is and all kinds of other things. It could even be pointing down for all we know. But it doesn't matter, because whatever it is there, it's going to be the same at all these positions at the same X, and it's going to be the same for all these positions at the same X at the bottom. Oops. This helps us. How does it help us? Top and the bottom are, so where does the area vector point in the top? Well, there is our dA vector on the top, and there is our dA vector on the bottom. They point out of the cube. So whatever is happening on the top, if you integrate along this particular line, you're going to get some value. If you integrate along the line at the other side of the cube, though, you're going to get that same value with the opposite sign, because the dA vector is pointing in the opposite direction. And so whatever comes in to the cube at the bottom must, in equal magnitude, exit the cube at the top. And even though the electric field value is changing as you move in X, it's still true that you have a top and a bottom part of this cube where they are exactly canceling out in every single X, dx you could imagine. So whatever E dot dA is on top must equal the negative of that value on the bottom. And I put a negative sign in there and I can't really read it. On bottom, on top, equals the negative of this on the top. So when you add them together, the total E dot dA is equal to 0. This works for any other possible shape, spherical shape you can think of, because any spherical shape you can make up by an infinite number or some very large number of very small cubes. And so any shape that you could have has to be the case that the total integral of E dot dA is 0, because any fields that are coming in will also be going out. That is almost analogous to the first proof on the homework that you have to do. It's the magnetic field instead of the electric field, but it's going to look very similar to this. So a nice diagram and some explanatory words are pretty much all you need for that one. Okay, so that's good. These fields satisfy Gauss's law, no problem. How about Faraday's law? Faraday's law, you might remember at least, is this. I was told that you may not have seen this big phi term before. That's okay. This is the magnetic flux. It can get really complicated, but basically, if you've got some magnetic field and some area, unless you have some weird changing magnetic field over some area or some weird geometry, this is almost always going to be the strength of magnetic field times the area of the loop that it's going through. That's really all it is. And that's all that we're going to be thinking about it in this class. When you get to E&M as a junior or senior, you'll think about much more complicated situations, but we don't ever have to worry about any of that. So for now, this is just magnetic field times the area of the thing, of the loop or the circle or whatever it is you've drawn that it's going through. Okay. So this example that I'm about to do is in the textbook. It's confusing though. So let's go through it also here today, and you can ask questions as we go, because this is actually really important and really cool. So let's go back to the diagram. This is going to be helpful. So we want to know, again, what a Faraday's law. You can imagine all kinds of different loops, but let's specifically ask about a loop in the xy plane. Is Faraday's law satisfied by these fields for a loop in the xy plane? So here we've got a loop in the xy plane, and we've got some point P that is in the middle of that loop. Okay? It's got, again, we're not going to worry too much about what these numbers are. We hope they're going to go away. We got some width of this thing dx, so that our field, it's very small, so that our fields aren't changing too much from one side to the other. And we've got some height of this loop h. Okay? And we're going to let this electromagnetic wave, which is exactly as we've described it before, traveling in the plus x direction, electric field in the y direction, magnetic field in the z direction. We're going to let this wave pass by. We're going to imagine what this wave looks like as it passes point P. Specifically, this section of the magnetic field with the red dot right here. So we're going to let this wave continue to propagate to the right until this dot right here, this red segment here, passes the point P. And that's where we're going to pause our simulation, our mental simulation, and think about whether or not Faraday's law is satisfied at that moment in time. Okay? So, let's think about Faraday's law. Let's go back to Faraday's law. We've got an electric field, we've got a changing magnetic field that's causing an electric field. That's what Faraday's law says. If you have some loop and the flux through it is changing, then you're going to induce an electric field. Well, that's interesting. We've already got an electric field. There's already an electric field pointing in the plus y direction. And we also have a changing B field and a changing B flux. So, what we know is that how the E field is changing, right? So again, we can talk about one side of this loop and the other side of this loop. On the leading edge of the loop, the magnetic field and the electric field are stronger at this particular moment when that red segment goes by. On the trailing edge, the electric fields and magnetic fields are a little bit smaller. So we could write down this equation. Well, we can write down this is the geometry of the loop that we're thinking about as that red segment passes by, right? We know that there's some E field pointing in the plus Y direction. We know that there's a slightly larger E field on the leading side, E plus DE, than there is on the left side. And we know that there is some magnetic flux, some magnetic field pointing out of the page that is some value B. And it's changing slightly across there too, but it's more changing in time. And that's really what we're going to be interested in looking at here. So we know, we'll come back to this in a minute, that E plus DE, let's actually draw that on this page too. This is that loop in the XY plane. XYZ. Okay. And we know that there is a electric field E. I've actually done this. What did they use? They use the same colors so we don't get confused. They use blue for the E field and green for the B field. Great. So here is the E field pointing in this direction. On this direction, we know that there's a slightly larger E field. Let's call it E plus DE. E plus DE. And we know that E, the magnitude of the electric field on the left, must be less than, I wrote a greater than, must be less than the magnitude of the E field on the right-hand side. So DE is positive. Right? We also know that there's a magnetic field that's coming out of the page. Great. So let's do the left-hand side of this integral. We know we got the integral of E dot ds. Let's go counterclockwise around the loop. Okay. So again, here's our loop. We're going to go counterclockwise. What is the value of this integral along the top of this loop going left? ds is pointing in this direction. What direction is E pointing in? Up in this particular case. Those are two vectors that are perpendicular to one another. So the top part, the integral over the top of this segment has to be 0. Same is true of the bottom. It's really only the left and the right that we have to worry about. Right? So let's go in this direction, and in this direction, and in this direction, and this direction, and this direction. Great. So top and bottom. Right, so you can really break this up into each of those different segments and then add the segments together. The top and the bottom are 0, those terms just go away. Since E is perpendicular to ds, and that dot product is 0. Now, on the left and the right-hand side, we're not so lucky. Now, when we go up, on the left-hand side, E and ds are parallel, and they're anti-parallel on the way back down. But they're parallel, so that dot product just becomes a regular product, and we don't have to worry about the vectors. That's nice. And the E field is constant along that entire leg, on the way up and on the way down. So the integral goes away too. We can pull E out of the integral, and the integral of ds is just the length of that side of the box. Right? Again, we're always setting this up so the integrals become easy and the dot products become easy. So on the right, integral of E dot ds is just integral of E times ds without the integral, without the vectors there, because they're parallel. And that is just the integral of E ds. And that is just E times h, which is the length of the vector. Now, I haven't put in the E field, and this is a little bit confusing because the E field on the right is not E, it's E plus DE, right? This is really E plus DE times H. That's the right. And on the left, we have exactly the same thing, except except that the E field is pointing in the up direction and the ds vector is pointing in the down direction as we move around the loop. And so instead of E times ds, we really have negative E times ds, since you're going in the other direction. And this is negative since E and ds point in opposite directions. That make sense? So the whole thing, as you go from completely around this loop once, you get 0 on the bottom, you get E plus dE times H on the up, you get 0 on the way on the way up across the top, and on the way back down, you get negative E times H. Add all those up, what do you get? The total left-hand side of the equation, total integral of E dot ds over all of the sides is just EH so let's expand this term out here. The right-hand side of the loop is EH plus DE times H. This is EH times DE times H minus the left-hand side, which is just EH. The EH's go away, and we've just got the total left-hand side is just H times DE. As we go around the entire loop length. I'm seeing some blank stares. It's EH, yeah, plus, you're right. You're right, I put a times there instead of a plus. This should be a plus. Yep, sorry. Hopefully that's what the blank stares are about. H is just the height of the, that's right, it's the integral of ds over the entire length up or down, right? It's the length of that, it's the length of that side of the box, that's right. It's the height of the box, so we called it H. Other questions? Again, this is a very complicated thing to do. We're taking surface integral, loop integrals of dot product vectors. But the way we've set the geometry up, all of that stuff becomes pretty simple. Yeah, so I said we're going counterclockwise around the thing. It doesn't really matter. If we had gone in the other direction, you would have gotten exactly the same answer, except it would have been a negative H times D instead of a positive H times D. It doesn't really matter. It's going to work either way. But the EH terms will cancel no matter which way you go, because you'll have a positive going in one direction and a negative going in the other direction, no matter how you go around it. And the E field will always be pointing in the same direction. Does that make sense? Good questions. Others. Okay. So that's the left-hand side of, what does the right-hand side look like? The right-hand side, what is the magnetic flux? Well, we already decided this is just B times A for our particular orientation. We know that the B field is some B. The area is just the height times the width, which is H times dx. Now, the B field will be changing slightly as we go by there, but we're not too worried about that. It's gonna be changing a very small amount as we go by. Let's shove that small inconsistency under the rug, because it's not really gonna matter at all. So this isn't the right-hand side completely. We need the negative of the time derivative of this thing, right? So negative sign's easy, just multiply by -1. Now you need to take the time derivative of this thing. Well, H isn't changing with time, that's a constant. Dx isn't changing with time, that's a constant. We can pull those out. And now all we need is dB dt. And that will be changing with time. Okay. So we now have both of these. We have the left-hand side. We can set that equal to the right-hand side and see what we get. The right-hand side was really easy. Let's equate the left-hand side and right-hand side and see where that gets us. We have that h times dE is equal to negative h times dx times dB dt. And nicely, we don't care how big we made this loop. The h's go away. They cancel out. So interestingly, this becomes dE equals dx times dB dt. Or, and this always weirds me out that you can just multiply derivatives and make derivatives go around, but you can. Differentiating works almost exactly the same as multiplying and dividing. We can make this, we can divide both sides by dx. What does that give us? dE dx, I forgot the negative sign, is equal to negative dB dt. That's interesting. What is that? How is that possible? The derivative of the E field is equal to the negative of the derivative of the B field. Aren't these exactly the same fields? How can one be negative of the other? Well, we're taking, yeah, go ahead. What? We're taking the derivative with respect to different things. So what have we said? Well, this is what must be true if Faraday's law is satisfied for these fields. It must be true that dx, dE dx must be equal to the negative of dB dt. So let's actually, we know what these fields look like. We have equations for them. We can take the x derivative, we can take the time derivative, we can set them equal to each other and see what that implies, shall we? So dE dx is k times EM, again, removing the vector part of it, just the magnitude of the electric field, times the sine of kx minus omega t. Great. dB dt is equal to negative omega times Bm times sine of kx minus omega t. Taking the negative omega out. Right? Set those two things equal to each other. K EM sine kx minus omega t is equal to the negative of the negative, the negative signs go away, of omega times Bm times sine of kx minus omega t. Signs go away. It's on both sides. We can divide through. That's cool. What do we get? KEM is equal to omega Bm. Or the ratio of the electric field, the amplitude of the electric field to the ratio of the amplitude of the magnetic field is equal to the angular frequency divided by the wave number. What is omega over k though? It's the wave speed. Omega over k is the wave speed. The angular frequency divided by the wave number is the wave speed. In this case, the speed of light, c. And I'm gonna give that an exclamation point, not because it's factorial, but because that's a kind of a whoa moment. If it is true that Faraday's law is satisfied in this region for these fields, then it must be the case that the ratio of the electric field to the magnetic field is equal to the wave speed. And that is the speed of light. That's pretty cool. So we know the speed of light is really fast, right? That's a number that's like 3 times 10 to the 8. So is the electric field just way more strong than the magnetic field for these electromagnetic waves? You want to say yes, but your intuition is telling you no, and that's good intuition. It is not the case that the electric field is way stronger than. How do you even assess the relative strength of two fields that have completely different units? How would you go about assessing the relative strength of those fields? How would you even make that comparison? There is a way. There's a good way to do it. Yeah, its ability to do work. It's energy, if you like. And we can calculate the energy associated with fields. And it turns out with that factor in there, that makes it so that the energy associated with the electric field is exactly the same as the energy associated with the magnetic field. They are identical. They sort of have to be identical. This is a self-propagating wave. The change in electric field is inducing the B field. The change in the B field is inducing the electric field. They have to be working together in perfect harmony, or the thing doesn't work. So the amplitudes, even though they have completely different units, work out to be the same if you think about the energy associated with both of those amplitudes. Make sense? Okay. And the homework, you're gonna do the other three other. So there's gonna be the Gauss's law one, and then the other two are different versions of this loop, and different. I don't know if they're both Faraday's law or not. They might be. It's much simpler than the one we've just done here. The two you have to do in the homework. And the big hint that I'm going to give you for the homework is the two proofs that you have to do both turn out to be proving that 0 equals 0. The left-hand side of both of them will be 0. The right-hand side of both of them will be 0. Your job is to prove to me that you understand why the left-hand side is 0 and the right-hand side is 0. Okay? There will be no thing left over to do interesting things with when you get done with the particular. The hardest part of both of these proofs is drawing the right diagram with the, you know, we did one in the XY plane, there's one in the YZ plane, there's one in the, I don't even remember where they are, but they're different versions of that same loop, just moved in different axes and directions, okay? So be careful. Make sure you understand where the loop is before you, and make sure, I think one is Faraday's law and one is Ampere's law. Make sure you're doing the right one. Make sure you're using the right equation and proving the right equation. Those are the two biggest mistakes that people make on these proofs. Put the plane in the wrong direction and use the wrong law. So just be careful with what you're doing. The other piece of hint I'm going to give you for the homework is 14. This is when you have 15 tries on. You have to write an equation for a wave of the electric field given its frequency and all kinds of other things. The hint that I'm going to give you there that's a little bit tricky is watch out for the initial condition of the wave. You're given in 13 that at t equals 0, the wave is at an amplitude maximum. This is not a sine function. Sines have minimums at t equals 0, x equals 0. So there is another function which is at a maximum at t equals 0, x equals 0. That's the one you should be using for this particular case. Everything else, other than that, it's pretty straightforward. So that's the big hint I'll give you for 14. And there are several other things you have to worry about, but everything else is laid out pretty much. Make sure you read all of the fine print in that problem, because there is some fine print there. And you need like 4 sig figs and all the numbers that you put in there too, so be aware of that. Okay, in the 5 minutes I've got left, I'm not going to do this. Again, it's in the book. You can go and look at the arguments that they make to do this, but you can do the same arguments using a Ampere's law for a plane, for a loop in the XZ plane. And the arguments work almost exactly the same, except switching magnetic and electric fields for that. And when you get to the end of that derivation, you get to, if Ampere's law is satisfied, then it must be the case that the ratio of the electric to magnetic fields, amplitudes, is equal to 1 over mu naught epsilon naught c. It follows almost exactly what we just did, except the constants out front are a little bit different. So these both must be true. Both this and this must be true if Ampere's law and Faraday's law are satisfied for these electromagnetic plane waves in a vacuum. And if both of those are true, then it must be that C is equal to 1 over mu naught epsilon naught times C. EM over BM equals C, which also equals 1 over mu naught epsilon naught C. And that tells us, multiply both sides by C, that C squared is equal to 1 over mu naught epsilon naught, and that C is equal to 1 over the square root of mu naught times epsilon naught. And those are constants. Maxwell's equations predict what the speed of light has to be in a vacuum. It must be that that is the case if Maxwell's laws are satisfied for electromagnetic waves propagating through a vacuum. That has to be true. Comes right out of Maxwell's equations. Maxwell's equations, in fact, predict what the speed of light will be. Okay, that's basically what else I want to do. Yeah, I've got a minute left, but it's not worth starting another topic right now. So enjoy your free minute today. Don't spend it all wastefully. Do something productive with it. Homework again is due tomorrow evening. I've got office hours tomorrow morning. Reflective writing assignment is due Friday morning. So enjoy the rest of your week. Let me, you're good.